So good afternoon, everyone, and welcome to our seminar today titled Algebraic MultiGrid Preconditioners for Sparse Linear Solvers at Extreme Scales on Hybrid Architectures. Our speaker today is Professor Pasqua Diambra, who graduated in mathematics summa cum laude at the University of Naples in 1990, and she earned her PhD in applied mathematics and computer science from the same university in 1995. She's CNR Senior Research Scientist with a permanent position at the Institute for Applied Computing in Naples. Her main research activities are in designing and developing numerical methods, algorithms, and mathematical software for high performance and parallel scientific computing. In this context, her main contributions are in the area of parallel numerical linear algebra and parallel solution of partial ordinary differential equations with applications to fluid dynamics and data analysis. A large part of the research results is freely available as mathematical software packages. Research activities are carried out within national and international projects where she plays principal investigator and work package leader roles. Professor Pasqua Diambra, thank you very much for being our speaker today, and we look forward to your talk. Thanks very much. Go ahead.
Okay, thank you. Thank you so much for the introduction, and thank you so much to Jacob and all colleagues from Cyprus Institute for the kind invitation to give this seminar. I am presenting activities for developing a scalable algebraic multi-grid preconditioner to be used in complex simulation codes at very large scale that are usually known as extreme scale. And our target machine are current and next generation supercomputers embedding hybrid forms of parallelism. First of all, I have to thank many people since this work is the result of collaboration and important discussion with people involved in my lab in different forms. And special thanks are also for Professor Panayot-Vasilevsky from the Lawrence Livermore Lab and Portland State University, with whom I have been working for many years, and Dr. Mantesh Alapanavar for the Pacific Northwest National Labs for sharing with us his code and its expertise on parallel graph matching we are using in our work. So let me tell you right away that our problem to solve is a sparse and large algebraic system of equations. It is a time-consuming kernel, you know, in many applications from traditional scientific computing to more recent area of data science, such as machine learning and artificial intelligence. Key issue in this context is the sparsity of the matrix, and then the need to use irregular data structure and memory and communication bound basic operations. Another issue is the size. You know, our problems are very large. The notion of large changes a lot in the time. Linear systems, which are perceived large in the von Neumann time, have less than 100 of unknowns, while in the late 2000s, we were able to solve in an efficient way system with 10 million of unknowns. And currently, we are facing the so-called exascale challenge. What is exascale challenge? We would like to use the current supercomputer targeting the next generation of computers, which will be able to do billions of flops for solving systems with more than tens of billions of unknowns. What is our driving philosophy in these activities? As we cannot expect to have a better performance just by improving the bottom technology layer, we have to concentrate on the top levels. Then we have to build better computer programming models, and even more, we have to concentrate on new algorithms, new mathematics, and new solution approaches, which could be able to exploit and take advantage by the new machines, which are characterized by many forms and many levels of parallelism and memory hierarchy. Just to clarify better where we want to solve our linear system, I just say that our target machines are in the list of the most powerful computers in the world. In particular, I am presenting today some results obtained on PixDyne, ranked the 15th in the last top 500 list. And then I also present results on Mare Nostrum. And I say that we are just moving on Marconi 100 for our experiment. I have to say also that our work is currently funded by two different European projects. We are involved in the ECO project, whose mission is to accelerate the transition to the production, storage, and management of clean, no-carbon energy. The project is organized around main scientific challenges in the energy sector and finds its roots in the high-performance community, since the final aim is to prepare selected applications to face the exascale challenges. So to be run in a efficient way on current and near future supercomputers. What are our target applications in ECO 2? Our problems are traditional computational fluid dynamics problems coming from wind simulation for wind farm application, and regional hydrological models on European ground. Here, our application scientists have to solve some partial differential equations of different types, and at the end, would like to solve sparse linear systems of more than 10 billion of unknowns by using the millions of cores, of parallel cores, in order to have reliable and high resolution simulation. The other project just started in April is the EuroHPC project named TEXTAROSSA, which is led by Enea, that is an Italian institution. Here, the focus is to propose a new software technology for finding the best trade-off between high performance and energy efficiency. And in this case, our role is played in order to design some kernels of a new mathematical library able to exploit mixed precision, communication avoiding algorithms, and all the new energy-aware programming tools proposed within the project by our partners. Okay, let's come to our activities. Our specific activities currently are focused on extensions and improvements of a software framework for parallel sparse computation, which for historical reasons is composed of three different components: PS+ and its plugin for using NVIDIA GPUs, and then more recent, the package AMG for PS+, which include parallel preconditioners based on PS+. Let me say that all the three components included in the PSC toolkit recently were selected as excellent innovations from European innovation radar. Okay, let me go inside. PS+. PS+ is a software development project which is started in the early 2000s. And it was stimulated by some work by Jane Duff and some of the co-authors of Duff, aimed to define standard application protocol interfaces for basic linear algebra operators involving sparse matrices, in the same light of some works having as objective defining application protocol interface for glass and dense matrices. The basic kernels of PS+ include functions for performing basic sparse matrix operations, such as the sparse matrix vector product, and it includes also some upper layer kernels implementing a large set of Krylov methods. The library also includes an infrastructure essentially to manage data storage and distribution of sparse matrices in a parallel setting. It has an algebraic interface where matrices are distributed in a general block way, which is consistent with the whole common usage of the widely used graph partitioners, such as MEPs, Sparse MEPs, which are also interfaced to PS+. If you want some details on PS+, you can refer to this paper from my colleague Salvatore Filipone and his co-authors on HCM ACM transaction on mathematical software. Okay, the library uses MPI as a distributed memory programming tool and is based on CUDA, NVIDIA CUDA, for efficient implementation of basic vector operations and sparse matrix vector multiplication on GPUs. The necessary data exchange patterns and the global to local index mapping needed in the parallel or basic operation involving sparse matrices are extracted in an automatic way from the matrix data and are provided as communication primitives. Particular attention was put in defining a scalable way which can represent distributed matrices, avoiding global description of the data that you know is unviable for increasing number of cores, of parallel cores. To this aim, PS+ uses a data structure named matrix descriptor, which stores all the information for inter-process communication required by the computation, only using additional memory requirements which are independent of the number of processors and increase only in a linear way in the size of the matrix. On the top of PS+, we design our library of preconditioners. So the software development project started in 2004 And the first release of the package only provided multi-level Sparse preconditioners. Then, currently, essentially within the context of the European project I just mentioned, we expanded the library with more general algebraic multigrid preconditioners. Then we expanded the library in order to have a layered software architecture, where at the bottom level we have CS Bus to manage parallel basic linear algebra computation. And in our development strategy, we apply a clear separation between user's interface and implementation of methods, exploiting, of course, operator overloading to maximize flexibility and modularity, oriented to an immediate extensions and also to the software we're using, and also to maximize performance at each layer. Another key issue we addressed was the simplicity of usage from the point of view of the user and the flexibility in preconditioner selection at each level of the setup and of the application. Okay, to better understand our package of preconditioner, I need to remind main feature of algebraic multigrid methods. And I apologize with whom of you are very expert in this context. Multigrid are efficient iterative methods for solving large and sparse linear systems. And they derive their efficiency by a recursive application of a two-grid process, which essentially consists of some smoother application and a coarse grid correction. The smoother application is generally based on iterations of some simple relaxation method, such as the Jacobi or the Gauss-Seidel method, while the coarse grid correction consists in the solution, in an approximate solution of the residual equation on a lower dimensional space. The obtained solution is then transferred back to the defined space by using a suitable prolongation, and then it can be still improved by some other iteration. The idea is that the smooth error components of the problem, which are not well reduced at fine level, can be dumped at the coarser level. Multigrid originated for solving systems coming from partial differential equations, where geometry and grids are already available. While we focus here on that extension of multigrid methods, which were designed for more general systems. For example, for systems which are not originated from PDEs, but for data science, for example. They are called algebraic multigrid, since only relies on matrix entry to set up the method. That is, to choose the coarser spaces of unknowns from the fine one, and to set the prolongation and restriction operator. Okay. Generally, multigrid methods are applied as preconditioners to accelerate convergence of iterative Krylov-subspace. Having a scalable preconditioner that in this slide is represented by the matrix B, the operator B, which can be promising for exascale computation, results in some stringent requirements for these operators. The ideal preconditioner operator produces a preconditioned matrix whose condition number is very small and hopefully is independent of n. This is what we call algorithmic scalability, and results in a constant and most constant number of iterations of the Krylov solver for increasing problem size. Furthermore, the cost of the application of the preconditioner should be linear in the problem size. That is, should be optimal from the point of view of the computational complexity, both in terms of flops and in terms of memory requirements. And last but not least, of course, it should be composed by local actions, which can allow the reduction of data communication among parallel processors, and leading to ideal performance or scalability in terms of implementation, which are performance linearly increasing for increasing number of processors and sites and problem size. The challenge for multi-grid methods on supercomputers is the possibility to translate an efficient and robust serial algorithm into a robust and scalable parallel algorithm. Good numerical properties need to be preserved when we make algorithmic changes imposed by the need to parallelize the operation. This is a non-trivial task and affects all aspects of a multi-grid algorithm, including coarsening, interpolation, and smoothing. The main parameters which we use as performance measure for multi-grid methods include the convergence rate, which affects the number of iterations of the solver, and the operator complexity, which is the number of non-zero of all the matrices of the algebraic MultiGrid hierarchy to the number of non-zeros of the original matrix. And these affects, of course, the computational complexity, both in terms of memory footprint and in terms of the application of the preconditioner in the solver phase. Both convergence factor and operator complexity need to be considered when we define the coarsening and interpolation procedures. Increasing complexity can give better convergence rates, but of course, the user needs to decide what is the priority in its application. Finally, another parameter is the stencil size, the average stencil size. That is the average number of non-zeros per row in the coarse matrices we built during the coarsening. It affects computation and communication in basic sparse matrix operations that are needed to apply both in the setup and in the application of the method. A small stencil size, of course, is good. However, also in this case, a small stencil of the coarser matrices has to be balanced with the convergence properties needed. In our case, in AMG for PS+, our precondition can be obtained by different combination of many methods and software models in order to face a larger set of users' needs. For setup, of the algebraic multigrid hierarchy, we have two different approaches, both based on aggregation of unknowns. We have a parallel implementation of the classical smoothed aggregation scheme from Vanek and Benzina that is based on a decoupled strategy where each parallel process applies the same algorithm to its local submatrix. Furthermore, more recently, we proposed a new parallel coursing based on a coupled strategy, which takes into account global connection among the processes, and it relies on an aggregation scheme based on maximum weight matching in the adjacency graph of the matrices. The aggregation scheme is named forcing based on compatible weight matching, and was developed in some recent work. For the solved phase, we can choose among different types of cycles, such as classical G, W, Krylov-based cycles, and a large set of smoothers and coarser solvers. I wrote in red the smoothers and the coarser solvers, which are already available for GPU computation in a hybrid programming model that we can use at the moment in the solved phase. And they include many versions of block-Jacobi methods, then the so-called hybrid Gauss-Seidel and additive Sparse. At the coarser level, we can use some parallel sparse LU factorization coming from third-party software interface to our library. And we also have the possibility to use all the version of inexact block-Jacobi smoother, and we also include the possibility to apply iterative Krylov solvers in a recursive way in order to enlarge the scalability of the coarser solver. Let me focus on our choices for smoothers. You know that a good smoother in classic algebraic multigrid is the Gauss-Seidel electrician method. You know that Gauss-Seidel is based on the splitting of the matrix, of the system matrix, and at each iteration, you need to invert a triangular matrix. You need to apply a triangular solution operation, which is intrinsically differential. So it is not so good in a parallel context. And we moved towards methods which can expose more parallels. These are different versions of inexact block-Jacobi, which include the so-called hybrid Gauss-Seidel, which is a form of the Gauss-Seidel algorithm, acting as the standard Gauss-Seidel within the local row block assigned to the process, and act as a Jacobi across the blocks in different processes. This is a version of Gauss-Seidel implemented, for example, in Boomer AMG, that is the preconditioner package for the Hydrological library at the Lawrence Livermore Lab. The standard Jacobi method, of course, is a particular version of the hybrid Gauss-Seidel. Then we also have the so-called L1 versions of Jacobi and Gauss-Seidel, which are more robust versions of the previous ones. Indeed, starting from the usual splitting of the local matrix block, we can define a local smoother by adding to the local Gauss-Seidel smoother a diagonal weight depending on the L1 norm of each row, so that the final smoother has the following diagonal block iteration matrix. Finally, inexact block Jacobi smoother, which rely at the block levels on some approximating indices, are also supported. And this choice is a good player, for example, together with the standard Jacobi on GPU accelerator, as they only rely on sparse matrix vector product, whose efficient implementation can be obtained for GPUs, and in our case is included in the PS Glass plugin for GPUs. Let me focus now on the parallel coupled coarsening scheme based on the maximum weight matching, which was first proposed in our software framework. It is based on the recursive application of a two-level hierarchy method, which exploit concept and results of a theory that is a theory for general coarsening and smoothers without using any a priori knowledge of matrix origin and smooth vector character that are usually used in the standard coarsening scheme. In particular, we propose a hierarchical method in which the fine space is decomposed as a direct sum of two orthogonal subspaces, a coarse space and a complementary space, which correspond to different prolongator operators. Starting from this space decomposition, we can have a block form of the original matrix, where the main diagonal block can be seen as a coarse matrix and its hierarchical complement. The general convergence theory, which we refer, was first introduced by Hardy Brandt and then well developed by Falgu and Vasilevsky, essentially exploit the principle of compatible relaxation and indicates that our subspace decomposition can define a good quality coarse matrix C if this second block, this complementary block, is very well conditioned. That is, a relaxation method applied on AF is very fast, and it corresponds to this requirement. So, starting from the above principle, we proposed to define a coarsening based on aggregation of unknowns, where the aggregates are obtained by weighted matching in the adjacency graph of the original matrix, so that the block AF can be as diagonally dominant as possible. In this way, relaxation on the subspace represented by AF is very fast, and it is a metric telling us that AC can be considered a good quality coarse matrix. Okay, maybe you know that the interaction between sparse linear algebra and combinatorial analysis has a long history and find its basis in the representation of sparse matrices in terms of undirected graph or bipartite graph. Starting from the undirected graph associated to our symmetric matrix, we consider this real weight matrix AF, which is obtained as linear combination among original matrix entries and the entries of an arbitrary vector W, which hopefully can be considered as a good representation of the smooth vector for our system. In this setting, a matching a matching in G is a subset of the age set in which there are not adjacent edges. That is, any two edges doesn't share a vector. We call a maximum weight matching a matching which maximizes the sum of the weights. Starting from a maximum weight matching, we split the original graph in that set in some subsets made of matched vertices and possible singleton related to possible unmatched vertices. Okay, after we obtain the aggregates, which are paired vertices or singleton, we can formally define a prolongator which represents a constant piecewise operator, in which each element corresponds to the orthonormal projection of the vector W on all the aggregates. Actually, we consider a log transformation of the weight in a hat in order to get a maximum product matching, which produce diagonally dominant AF for construction. And we use in this case some papers which are well known in sparse linear algebra, as they are used in direct methods to avoid or postpone pivoting strategies in LU factorization and are devoted, of course, to produce the dominance of the diagonal in a permuted matrix. So starting from these results in the literature, we call these strategies. At the end, we can summarize the coarsening algorithm, which we referred as compatible gradient matching. Starting with the given system matrix and an arbitrary vector, we can consider a pairwise aggregation scheme, and we can build the integrate operators, the prolongators, and these transpose, and then we can compute the coarse matrix by the standard Galerkin approach. At each, this procedure is applied in a recursive way until the size of the coarse matrix is not larger of fixed size, and or when the number of levels are sufficiently high. And at each level, we consider the projection of the vector W in order to restart the procedure by applying the parallel matching to the graph of the current level matrix, depending on the restriction of the W vector. We can increase the coarsening ratio of our coarsening procedure by the product of consecutive prolongators corresponding to pairwise aggregation. For example, we can do a double pairwise aggregation by combining two consecutive prolongators, and in this case we obtain aggregates of size at most 4. Main computational terms in these algorithms are matrix-matrix multiplications related to the Galerkin computation, but also to the combination of consecutive prolongators, sparse matrix vector multiplication, And finally, parallel matching, parallel algorithms for the computation of maximum weight matching in a weighted graph. While in PS Plus were available all the functionalities for the sparse matrix operations, we needed to have an efficient parallel implementation of the maximum weight matching for setup of the coursing. Algorithms for optimal matching available in the literature are very expensive. They have generally a superlinear complexity and are intrinsically sequential, since are based on the Hungarian algorithms. Therefore, we decided to relax the request on optimality and look for near optimal solutions. There are many approximation algorithms which can guarantee the quality of the computer matching. In particular, they are able to find in linear time complexity a matching whose total weight is at last the half of the optimal weight, and they are called alpha approximate matching. The good thing is that parallel implementation of some of these algorithms are available in source 4 within the Matchbox P software framework. It is a product of research of Mantesh, Shalapanavar, and Alex Botan and their co-authors. And we get an efficient implementation of a half approximate matching, first proposed by Praise, and then implementing the Matchbox P in an efficient way, and integrated it in our package in order to finalize the setup of our coursing based on compatible with the matching. Let me summarize the main advantages of new matching. It is compatible matching and we call C-match. Main advantages of the new coursing with respect to all the currently available aggregation schemes are that it is a completely automatic procedure and is independent of any heuristic or a priori information on the near kernel of the matrix. On the other hand, our coupled parallel implementation produces well-balanced coarse matrices among the processor, and there is no need for special treatment of boundaries as in the standard coursing based on matching. And furthermore, there is also a flexibility in the choice of the size of aggregates, since we can apply the coursing in more sweeps of phase weight aggregation by multiplication of consecutive elongators, obtaining an arbitrary aggressive coursing. Let me say that we can apply the coursing as a plain aggregation scheme by using the piecewise constant prolongators coupled with a robust cycle such as a cycle in order to obtain optimality convergence and preserving memory requirements. But we also could apply some smoothing of the matching-based prolongator, as in the classical smoothed aggregation schemes, in order to couple our prolongators with a standard and cheap D cycle. In this case, suitable choices in sites of aggregates allow us to obtain a good trade-off between complexity and convergence. Okay, let's go to some results. We tested the weak scalability of our software framework on many problems, and in this presentation I give results on the standard Laplace equation, on unit cube with the Dirichlet boundary condition. The equation was discretized with the standard 7-point time difference scheme on a Cartesian grid that was uniformly refined in order to obtain systems with increasing size. The resulting system was solved by a flexible version of the conjugate gradient method, and we consider different types of preconditions. We consider a K-cycle with 2 inner iterations at each coarser level, which is based on our coursing based on matching, where unsmoothed prolongators are applied. In the second case, we consider the same coursing, but here we couple the scheme with the smoothed prolongators, and we use B-cycle in the application. And finally, for comparison aims, we also report results obtained by the already available decoupled classical smoothed aggregation coupled with B-cycle. The coarsening was stopped for all the coarsening schemes when the size of the coarser matrix was not larger than a fixed size depending on the number of parallel cores. This choice is justified by the need to avoid to have a very deep hierarchies, which is not desirable in a parallel computing environment, where you know that the cost of data communication can become relevant when we go up to the coarser levels. In our test, we consider ever one sweep of forward, backward, guided outside smoother as a pre and post smoother, and we decide to apply an iterative solution of the coarser system by using in a recursive way a parallel conjugate gradient at the coarser level, preconditioned with a block Jacobi with the incomplete LU factorization on the local blocks at the coarser level. So I show results obtained on fixed line and compare our preconditioner with some of the most widely used parallel preconditioner available in the ITER code. For our aims, we choose three different coursing schemes showing different complexity and scalability features as recommended in the user guide of ITER. And we apply all the hierarchy in the same way as our preconditioner. Indeed, we use the cycle with the same choice of smoothers. We know that in this case, the coarsest matrix the coarsest matrices have a very small size. Indeed, the coarsening scheme by Harper obtained a very deep hierarchy, since they apply an aggregation of the coarse matrix on a small set of parallel processes in order to have a scalable solution at the coarser level. Okay, we did a weak scalability analysis by using a grid or a mesh with the fixed size process, so that the local matrix has 256,000 rows. I show here results using up to 27,000 cores, leading to to a global matrix of more than 2 million, we can see that our new coarsening produce a good quality recognition, which shows a very small increase in number of iterations for increasing cores, both in the case of K cycle and in the case of the cycle. Unlike the uncoupled smoother aggregation, show a significant increase for large number of cores in the number of iterations. The behavior of our preconditioner based on recycle and on compatible weighted matching by using a smoother prolongator is very similar to the preconditioner in hybrid, which is based on the so-called Falgout coarsening, which appear as the most robust of the three coarsening we selected. Let me say that this small increase in the number of iterations when we use 2 to 11 cores is related to a deterioration of the quality of the aggregates due to the size, to a specific combination in the number of the cores and the size of the matrix, while this increase does not appear in the other configuration. So we can consider our coarsening scheme very, very robust and with very good algorithmic scalability properties. Let me go to the operator complexity. What is the cost of the application and what is the cost in terms of memory footprint of the preconditioners? We can see that our new coarsening, when it is based on unsmoothed prolongator that are very cheap, show the smallest operator complexity, that is just over 1 for each number of cores, and it is comparable with most cheap hybrid coarsening, that is HMIS1. On the other hand, if we consider our smoothed aggregation scheme based on matching, we have a small increase of complexity, although these remain under 2, while on the contrary, the Falgout and the HMIS coarsening produce very expensive hierarchies with very large cost and memory footprint. Let me go to the solve time. That is the time of the application of precondition inside the Krylov iteration. We can see that our precondition based on compatible weighted matching have the best execution times, and generally best execution time for increasing cores. It is smaller than all the hybrid preconditioner. It is this yellow, blue, and red, and is also smaller of the other two preconditioner by AMG 4PS+. We can see that the preconditioner by AMG 4PS+ based on K cycle have an execution time which increase with number of cores, and this is not strange since implementation scalability of a K cycle pays the needs to visit a large number of times with respect to the V cycle, the coarsest levels of the AMG hierarchy. Let me observe that when we analyze weak scalability, As in this case, we would like to see flat lines. That is an execution time that is almost constant for increasing number of cores and sites in a linear way. While we see here a slowly increasing line. This is not strange for this type of problem, which are memory and communication bound, and then the memory and data communication bandwidth saturation limits the overall scalability. We don't see ideal flat lines, but let me say that we can see that the time increase in a very slow way. And we can see, of course, that we outperform similar reference methods. Let me give a look at the time for setup of the preconditioner. We see that the coarsening based on weighted matching in the light blue line and this line are a large setup with respect to setup time, with respect to the high preconditioners. But anyway, if we take into account the large reduction in memory footprint and in solve time, we can say that our preconditioner span a small increase setup time to obtain very effective preconditioner. Indeed, that small increase in the setup time of an algebraic multigrid hierarchy is usually well tolerated in time-dependent or non-linear application where the same preconditioner is used for many time steps or many iterations. In this slide, I like to show some results obtained in going up to more than to 27,000 of MPI cores for increasing mesh size per core up to a global system of 10 billions of unknowns. In the same picture, we can also see two lines related to the red lines and the blue lines that are related to results obtained running the solve phase on GPUs. In this case, we substitute the hybrid Gauss-Seidel with the L1 Jacobi's model. We used up to more than 2,000 GPUs that are the Pascal GPUs of fixed times, and we use that at maximum speed. Let me also observe that we are solving a system of sites that is more than 2,000 times the sites we have on one GPU, with an execution time that is only 10 times more. Indeed, here on 2048 GPUs, we are solving a system of more than 10 billion of unknowns in less than 3 seconds. And these allow us to obtain a significant speed up with respect to the homogeneous CPU version based on CPU. And these allow us to obtain not only a speed up in solve time, but a large saving in energy consumption, since we are using a small number of parallel nodes in order to solve the same systems in less time. If I have a few minutes more, I like to present also some preliminary results obtained by using our libraries as integrated in a multi-physics code developed at the Barcelona Supercomputing Center. This is a joint work with our colleague Herbert Cohen within HECO. The ALIA code is used in ECO2 for wind simulations on comprehensive array. And we tested our precondition in the large eddy simulation of a turbulent wind flow, which generates around the ball wheel, that is an isolated wind in Denmark. And the numerical model is based on discretization of incompressible unstable narrow-state equation, and lead to a Poisson-type equation for the precious field. On this equation, we did some strong scale test for different mesh sizes on increasing number of the cores in different configurations. We analyzed the strong scalability of our solver in the full developed flow phase, and we consider the total number of iterations and the total time to solve the linear systems over 20 consecutive time steps. We compared the PS plus conjugate gradient coupled with the two preconditioners I used before with the deflated conjugate gradient available in ALIA. For our preconditioner, we use the same algorithmic parameters as applied before, but in this case, 4 switches of hybrid Gauss-Seidel are applied as pre and post mover. We ran the experiments on Mare Nostrum, only using the homogeneous MPI-based libraries on CPU cores. And if we look at the number of iterations for each mesh size and for each configuration of a processor, we see that our multi-grid preconditioner are able to decrease in a consistent way the number of iterations for solving the linear system in the pressure equation. We look also at the parallel performance in terms of time per iteration. We see that time per iteration decrease for increasing number of cores in this strong scaling setting, and as expected, the conjugate gradient included in ALIA for its one level nature as the smallest time per iteration. On the other hand, if we look at the total time, we can see that the gain in the number of iterations permits to the algebraic multigrid to obtain the best time to solution with respect to the original ALIA solver. We are continuing in these activities, and we are trying to increase mesh sizes in order to solve problems with more than 10 millions of unknowns, and we are doing these experiments currently on Marconi 100 in Italy, and on another supercomputer operated in the ULIC supercomputing center. Okay, let me go to some remarks and conclusions on this work. I presented the PSC toolkit, that is a new software framework addressing scalability, flexibility, and robustness in order to do high-performance scientific computing at extreme scale. Our new parallel coarsening algorithm based on compatible wave matching when is used in conjunction with smoother prolongators can have very competitive with other solvers, with other preconditioners. We solved systems with size larger than 10 million on current petascale supercomputers, embedding hybrid nodes in less than 10 seconds. And scalability results and comparison with the available software demonstrate the validity of our approaches. And we are working to integrate and test these software libraries in very large wind simulation and hydrological applications in collaboration with the Barcelona Supercomputing Center and ULIC Supercomputing Center, and the activities in progress in the ECO and TEXTAROSSA projects. Let me thank for your attention. I am ready for your question. I hope to have been clear and not boring. And this is the list of essential bibliography on our work. Okay, thank you so much.
Thank you, Professor De Ambra, for your talk. Thanks for your results also. You're making available to everyone. I was wondering if there's any questions from the people that who followed. So if there are, I'm sure there are. Okay, so Kiriago, well, whoever else has any questions, please raise your hands. Kiriago, please unmute yourself and go ahead. Thank you.
Hi, my name is Kiriagos. Thanks a lot for the presentation. So I wanted to understand better. You showed before the weak scaling. Okay, so you compare when using just CPU cores to GPU. And you said that there is an overhead due to the fact that the problem is memory bounded, if I remember correctly.
Yes, correct. You know that sparse matrices are based on irregular data structure, and the problem is that the number of non-zero per each row is very small. So usually the transfer of data from different levels of memory is very expensive, and this type of computation are limited in the scalability with respect to memory bandwidth saturation and data communication bandwidth saturation.
Okay, but to solve those differential equation, you do it. You have interior and exterior points that you need to use the. I mean, to do the calculation, right? I mean, you need information from neighbors.
Yeah.
So, in principle, you can overlap the communication with the computation. So to hide, let's say, up to some extent, this memory latency. So this is, yeah.
We can in some forms. We can in some forms, for example, in the implementation of a sparse matrix vector multiplication, that is basic kernels in this type of algorithms. And usually we consider the information on the halo points that are the points in the neighbor processor before to do computation inside. And in this way, we overlap in some sense computation and communication.
Okay.
This is an effort that we did in the basic kernels of the library, especially in the sparse matrix vector products.
Okay.
And the same was done in the parallel matching implemented in Matchbox P that we interfaced with our library. Indeed, in that case, the problem is very communication intensive, and the authors of the parallel algorithms for maximum weight matching need some type of overlap between communication and computation in order to improve scalability.
Okay, and my second question is that okay, you show us the weak scaling, but I was wondering about the strong scaling, where you have a fixed size of problem and you want to scale it to a bigger and bigger number of GPUs. The multi-grid does not lose performance in the sense that you have less and less workload to give to a GPU, which is a massively parallel unit.
Yeah, this is true. This is true. You know, I don't know if you have seen sorry, let me share again presentation. Here we have strong scaling.
Yes, I want to understand it better, yes.
A Poisson type equation. In this case, here we have the solve time. We have different mesh sizes, three different features for analyzing strong scaling by increasing the number of cores for the fixed size problem with the three different solvers. You see that when we use, of course, strong scaling analysis, when we do, we spend about the same time on 191 cores than we spend on 95.
So this is on CPUs, right?
These are CPU cores, yeah.
Okay, so you don't have this on the GPUs, this strong scale.
We don't have yet results on GPU for this test case.
Okay.
But if you consider this, the two lines, the red lines and the blue lines, you have two different lines related to different workload per GPU. Yeah. In the case of blue line, we have 6 million of unknowns per GPU. In the case of red lines, we have 3 million of unknowns per GPU. So, for example, here we have the same size, the same global size of the system solved on a different number of GPUs. And you can see that we have a similar, very similar times, very similar execution times. And this is due to the fact that we cannot have an increase in speed up when the GPU is used at the best speed, since the bandwidth saturation, the memory bandwidth saturation, and also the data communication limit from up the performance for the same size.
Okay.
We have to go deep inside on this aspect, but you know that it is well known, the lambda law, that in the case you increase number of cores without increasing the size of the problem, you limit the overall speed up by half, since the communication overhead becomes significant.
Mm-hmm.
And this is what we see on CPU cores, but this also appears in a more consistent way, in a more significant way when we use GPU.
Yeah. Okay, thank
you. Simone, you have a question?
Yeah,
also?
thank you. Yeah, Hi, I'm Simone, and thank you for the nice talk. I would have a few questions actually, but I can try to be fast. So when you now you showed a computer with CG, I didn't get if that is a regular CG or it's you had other things in the name. Maybe is it something more?
Are you asking about? Sorry, I didn't hear that well. Are you asking about the conjugate gradient?
Yeah. When you compared with the conjugate gradient, that's a pure conjugate gradient, or it's a variation of the algorithm.
In the results obtained on this slide, we used a flexible conjugate gradient, a flexible version of the conjugate gradient.
Wait.
That is coupled with our three preconditions.
Yeah, no, that I got it. Yeah, I mean the results from BSc from the Barcelona.
From the BSc, we used as for comparison aims the deflated conjugate gradient, a version of the deflated conjugate gradient implemented by the Barcelona Supercomputing Center.
Okay, so it's deflated. Yeah, I read that was the FSCG, so I was wondering if it was deflated. So
deflated,
it's,
yeah. I don't remember the specific details of the deflation. I remember that they used 1,000 groups, but I don't remember the details. If you want, I can check and I can send.
No, yeah, I was just wondering the speed up you get compared to a regular CG instead of.
We had also results with a regular CG without recognition. No, with diagonal recognition. That is also implemented in the area code. We put these results in the deliverable project and in the project deliverables, and we see that the situation is worse. Of course, deflated CG is better than diagonal preconditioned CG.
Clear. Okay, thank you. And then in these scaling plots cases you showed, I got you did some quite strict setup. I was instead in our case we use often multigrid, and for us it's very important to tune very well the parameters, because by changing one parameter one may gain several factors. So the question would be, how far away is this setup you used for the scaling from the optimal one you will get for that problem?
Oh yeah. Our philosophy was to do all the possible parameters in order to do the best tuning. However, in my experience, I see with our preconditioners, especially with the preconditioner based on matching, that is very robust and has many advantages in terms of the coarse matrix balancing among the parallel processor. The number of parameters to consider is related to the size of the aggregates, and a good size for aggregates on some standard problems such as Poisson 7-point fine difference equations is 8. Since 8 is the usual number coming from the aggregation scheme, which are well known in the literature, or are comparable with the size of coarse spaces when you use classical algebraic multigrid based on coarse to fine separation. And the other parameter is the smoothing. On the other hand, we use only one step of smoothing, since in this case we were able to have a small enough stencil on the course levels. So I think that you have many ways to tune the setup, but the main parameters are not so large in number. I don't know if I answered your question.
Yeah, no, it's fine. Yes, yeah, I was wondering just how far away was that, because usually in our case we always go, yeah, to very small grid, and then the scale is not so good once we coarsen a lot. So because then that one will gain really a lot of in the timing. So anyway, it's fine. It's okay.
Okay.
Thank you.
Thank you, Simone, for your question. Jakob, you're up next.
Yeah, thanks. Yeah, thanks for your interesting talk. It was nice to follow. I maybe just a question about the setup. Maybe I missed. I mean, I missed the timings. So how expensive is your setup compared to your solve times? Maybe can you?
Oh yeah. Let me share again.
Yes.
Okay. You can see, do you see?
Yes, yes.
This is the setup time for the preconditioners.
Mm-hmm.
This line and this line are our preconditioner. You see that the total time for setup in seconds is about 1 second, is no more than 2 seconds.
Mm-hmm.
Okay. On the other hand, if you consider solve time, in the similar case, we have less than 1 second usually,
So it's
and about
like,
1 second on 8,000 cores.
so it's something like 10% of the solve time is.
Yeah,
the
less than 10%. Yeah.
But this is now for this example. Is this different for other examples, or maybe another questions? Can you comment a bit on if you go to other different problems? Maybe can you comment on this, how to tune the setup for going maybe to, for example, this problem which you showed from BSc? How difficult it is to tune and to I mean to reach a working procedure.
Yeah. In the case of the Barcelona supercomputing center test case, we did experiments for the moment on the pressure equation in the LES, in the LES, and you know that in this case we have similar systems than Poisson type equation.
Mm-hmm.
And in this case, we used a phase for tuning the setup of the algebraic multigrid, in which we only changed the number of smoothing steps and the size of the aggregation scheme in order to balance the coarsening ratio of the aggregation scheme, in order to balance the memory requirements and the efficiency in the solve phase. We don't have yet experience, for example, on using these preconditions, our preconditions, in the case of more general systems coming from completely unstructured grids, or on weakly non-symmetric matrices, for example, coming from advection diffusion. So I don't know what are the possibility we have in terms of tuning in order to go in the same way for different problems. We have to experiment the coarsening and all the stuff on more difficult problem. Anyway, let me say that we also have results on preliminary results on the hydrological model included in ParFlow, that is the code used in Unix Supercomputing Center. And in that case, we have a large anisotropy in the system. And in this case, we have seen that our preconditioners are very robust in terms of anisotropy levels and anisotropy direction. So we expect that we can do good by using the flexibility in terms of cycle type, of aggregation schemes and sites, and of smoothers. We expect good results also for that type of problems. I don't know, for different type of equations or for completely non-symmetric matrices, we have not yet results, also because all the coarsening scheme we have now requires that the matrix has a symmetric sparsity pattern.
Okay, I see. Yeah, probably it's also for parallelization. If it gets unsymmetric, then it gets difficulty also in the parallelization approach. Okay, thank you.
You are welcome.
Thanks, Jacob, for your question. Does anyone else have a question for Professor De Ambra? It appears that this is not the case. In which case, I would like to thank our speaker for today. Thank you, Professor De Ambra, for your time and for your talk. And I am sure that people will be using your research in their work as well.
If you need information, feel free to write me when you try to use our software.
Okay. Thanks again for your time. Thank you all for joining. And we have another seminar next week, I believe, our last one for the summer. Again, thanks to our speaker, and goodbye, everyone.
Bye-bye. Thanks to you.
Bye.
Thank you very much.
Bye-bye. Thank you very much.
Bye.